Hello. Before we begin the Chapter 7.5 lecture on the Dirac delta function, I think it would be good to talk about one of the most missed and asked about homework problems from Chapter 7.4. It was this one. Your number might have been different. It's consider this differential equation with those initial values, solve it. And the homework problem gave you this hint. It reminded you that the Laplace transform of t to the n times f of t is this. So when we take the Laplace transform of both sides, first let me say that the Laplace transform of t times y prime is not equal to t times the Laplace transform of y prime because t is not a constant. You cannot pull it out. What the Laplace transform of t times y prime is by this theorem, -1 times dds of the Laplace transform of y prime. So this is the key aspect of the problem. So what happens? So this was our problem. We take the Laplace transform of both sides as usual. We use linearity. Laplace transform of 14 is 14 over s. Laplace transform of y double prime is, as usual, s squared f of s minus s times y of 0, which in this case is 0, minus y prime of 0. That's our theorem on Laplace transforms of derivatives. We'll leave this part alone for now. And another word for the Laplace transform of y is just f of s. Okay, now, this part. What do we do there? Well, we know by this theorem that it will be -1 to the 1 times dds of f of s, where f of s is the Laplace transform of little f of t, which in this case is y prime. So we have this. That is negative dds of the Laplace transform of y prime. And what is the Laplace transform of y prime? Well, by our theorem on derivatives, that is s times f of s minus y of 0. And here we were again told that that is 0 in the initial value. So we have negative d ds of s times f of s. And how do we take this derivative? Well, this is a product. This is f times g. So we'll have an f prime g plus f g prime by the product rule. The derivative of s with respect to s is 1. So we have 1 times f of s plus s times the derivative of f of s. So we have negative f of s minus s times f prime of s. So that is what that Laplace transform is. So after we take the Laplace transform of both sides, we'll have 2s squared f of s minus f of s minus s times f prime of s minus 2f of s is 14 over s. And now this is a first order differential equation. So we can now apply our chapter 2 techniques to solve this. So we got this, and this does not look separable, but it's linear. Rearranging it into our standard form for integrating factors, this is that. What we did there was we isolated that f prime of s by moving it to the front and dividing both sides by negative s, so that it became a positive f prime of s. And then we gathered together the two f of s terms. F of s minus 2f of s is minus 3f of s, but then we divided by negative s, and we wind up with that. So that's our rearranged form. And now this guy, that is our p of s, where recall that for integrating factors, our integrating factor is e to the integral of p of x dx, which in this case is p of s ds. So we compute that and recall our utilization of exponentiation laws to simplify this. And that is s cubed e to the negative s squared. So multiplying both sides of our differential equation by our integrating factor, and then undoing the product rule, that is s cubed e to the negative s squared times f of s prime is equal to s cubed e to the negative s squared times negative 14 over s squared. Or slightly simplifying the right-hand side, we have that. So now we integrate both sides with respect to s. Integral of the derivative cancels out, and integral of 14s e to the negative s squared is negative 7 e to the negative s squared, plus c. Don't forget that. And therefore, our Laplace transform is dividing both sides by s cubed e to the negative s squared, is that. And part one of the problem was asking for what the Laplace transform of y is, and that is the answer. And what is y itself? Well, something like e to the s squared, we've never seen a Laplace transform that looks like that. But we just want a solution. And when c is 0, then it just becomes negative 7 over s cubed. So what we can do is we'll just let c be equal to 0 and look at just the inverse transform of that and hope that it satisfies those initial conditions. And it will. So then y is the inverse transform of negative 7 over s cubed. And now this is a standard problem where we'll make this look like one of our known transforms by writing that 3 up there is 2 plus 1. We want a 2 factorial up there. We'll divide by 2 factorial. So we rewrite it in that way. And we have negative 7 over 2 times t squared. And you can verify that this satisfies the differential equation and the initial conditions. So our hoping that letting c be 0 would work availed itself, and it does. So that's the solution to that problem and how to do it. What I like about this is that before this whole chapter on Laplace transforms, we had no idea how to deal with second-order differential equations that had non-constant coefficients. Back in chapter 4, it was exclusively about constant coefficients. But with the magic of Laplace transforms and this derivative property, we can solve higher-order differential equations with non-constant coefficients as well. So that's pretty great. Now let's begin chapter 7.5 on the Dirac function. So chapter 7.5 is on the Dirac delta function. So take a look at our known transforms. We have 1 over s, things over s to the n, 1 over s minus a, 1 over s squared plus 1 squared, etc. But what is the inverse transform of 1? A simple 1 is missing from all of these known transforms. It will turn out that the inverse transform of 1 will be the Dirac delta function, which this section is about. Before we introduce it, we need to introduce the unit impulse function in terms of which it is defined. The unit impulse function, delta sub a, is defined as follows here. It's easier to understand this pictographically. It is a rectangle, essentially, of height 1 over 2a and radius a, and therefore width 2a. And therefore the area underneath it is base times height is 2a times 1 over 2a is 1. So therefore the integral from 0 to infinity of the unit impulse function is 1. There's no area here, and the area of this is 1, no matter what a is. And as a gets smaller and smaller, our unit impulse function looks like this. By the way, it's called the unit impulse because unit 1, area 1. So as the radius gets smaller and smaller, our height has to get taller and taller in order to preserve that this always has area 1. And the Dirac delta function, and calling it a function is a bit of a misnomer in the sense that it's technically a generalized function, is the limit as the radius a approaches 0 of the unit impulse function. So the Dirac delta function, you can think of it as like a rectangle of infinite height and 0 width with area 1. So it's not technically a function. It is a distribution that has area 1 underneath an infinitely tall, infinitely thin sliver. So for example, here's what the Dirac delta function of t minus 2 would look like. it is 0 everywhere except at 2, and at 2, it is a vertical line of sorts in which the area of this vertical line, you think of it as like a rectangle of width 0 and height infinity, approached in such a manner that the area stayed 1. So this is a rectangle, quote unquote, of area 1. Now, what is the integral from negative infinity to t of the Dirac delta function of x? So that was Dirac delta of t, or x minus 2. Dirac delta function of just x. That means it's unshifted. So it looks like this, in which we have area 1 right there. And what is this integral? So imagine as we're moving from left to right, accumulating area. So when we're at this point, for example, what is the area underneath the Dirac delta function to the left? Well, there is no area to the left. It's always 0 over here. So over here, our integral is 0, and it stays 0. What happens as we move to the right? Okay, we don't add any area. And what happens right here? How much area have we added as we have moved from left to right and gone just past this, quote, rectangle of area 1? Well, now we've suddenly added an area of 1. So what happens there is we jump up and suddenly have area 1. And as we keep going to the right, do we add any more area? No. Over here, there is no more area to add. So then it just stays at our having area 1 to the left once we're bigger than 0. So this is what the integral looks like. What function is that? That is the unit step function. So the integral of the Dirac delta function is the unit step function. So the derivative of the unit step function, it doesn't exist here. This is not differentiable. But if it existed, then in as much as this Dirac delta function has an integral that is the unit step function, the derivative of the unit step function would be the Dirac delta function. So the integral from negative infinity to t of the Dirac delta is the unit step function, and thus we can think of the Dirac delta function as what we would get by pretending that the unit step function has a derivative. So we know that the Dirac delta function is the derivative of the unit step function. So what is the Laplace transform of the Dirac delta function? Well, the Laplace transform of the Dirac delta function would be the Laplace transform of the derivative of the unit step function by this, as we found. And we know how to take the Laplace transform of a derivative. It'll be s f of s minus y of 0. In this case, that's u of 0. And unit step of 0 goes away. So therefore, the Laplace transform of the Dirac delta function of t minus t naught is that. But f of s here, that is the Laplace transform of the unit step function, which by our first derivative property, with f of t minus a being equal to 1, is e to the negative as, e to the negative st, times the Laplace transform of 1, which is 1 over s. So we have s times 1 over s times e to the negative s t naught is e to the negative st naught. So that is our Laplace transform of the Dirac delta of t minus t naught. Boxed here, and in particular, letting t naught be 0, then that means that the Laplace transform of Dirac delta of t minus 0 is e to the negative s times 0, and therefore the Laplace transform of Dirac delta of t is 1. So that means that the Dirac delta function is the inverse transform of 1, and that alone indicates that it has inherent mathematical significance. So how does the Dirac delta function manifest in real life? Here is Einstein whacking a golf ball. And we can think of this as him imparting, say, 1 joule or something like that over a very short period of time. So we have this diagram from earlier of imparting a non-zero amount of energy in essentially zero time, and we wind up with the Dirac delta function as our mathematical model. Or say that something is swinging on a pendulum, swinging up, back and forth, and then suddenly you take a mallet and whack it, and now it's swinging back and forth at a higher amplitude. So we could model that as a Dirac delta function occurring right there at time t equals 2 pi, imparting a non-zero energy in essentially zero time, whacking it into a different cycle with a higher amplitude. So it's through cases like that that we would wind up naturally with the differential equations that look like this. Y double prime plus y is 4 times Dirac delta of t minus 2 pi, resulting in a pendulum swing that looks like this. And we can solve that using our usual techniques by taking the Laplace transform of both sides and using our newfound knowledge of what the Laplace transform of the Dirac delta function is. So at this point, there isn't too much new, really. Not too much new in the sense that it's really just another function that we have added to our list of known inverse transforms. So for example, let's solve this differential equation. Y prime minus 3y is Dirac delta of t minus 2 with initial condition y of 0 is 0. So we take the Laplace transform of both sides, and that's s f of s minus y of 0 minus 3f of s, that's our left-hand side as usual, where y of 0 is 0, is equal to the Laplace transform of Dirac delta of t minus 2. But we know that Laplace transform of Dirac delta of t minus t naught is e to the negative s t naught. So from this, that will be e to the negative s times 2. So we have s f of s minus 3f of s is e to the negative 2s, and we factor out the f of s and solve. Factoring out the f of s, we have s minus 3. We divide both sides by s minus 3, and we have that. So then y is the inverse transform of this guy. Whenever we have an e to the something inside an inverse transform, that's begging us to use our second translational property. The inverse transform of 1 over s minus 3 is e to the 3t. So by our second translational property, this will be e to the 3 times t minus 2, because of that 2 there, times unit step of t minus 2, using that it's f of t minus a times unit step of t minus a, where little f is the inverse transform of 1 over s minus 3, which is e to the 3t. So we replace that t with our t minus 2 due to that 2 there, and we have that. And we solve the differential equation. So this is what I mean by nothing fundamentally new. It's just a new transform and inverse transform to add to our list, and then we deal with them in a usual way together with all the translational properties that we've already learned. Let's do one more. Consider this guy. Y double prime plus 10y prime plus 26y is Dirac delta of t minus 2 pi with those initial conditions. We take the Laplace transform of both sides as usual. So using our derivative rules and the fact that our y of 0 and y prime 0 are both 0, we have that. After we take the Laplace transform of the left-hand side via the derivative rule right there. Remember, those are 0, so those become 0, and we just wind up with s squared f of s there, and s f of s there. And Dirac delta of t minus 2 pi, that becomes e to the negative s times 2 pi. So now we factor out, and we have e to the negative 2 pi s times 1 over s squared plus 10s plus 26. And now we find the inverse transform of that. So think, how can we go about doing this? Well, whenever we have an e to the something in our inverse transform, that is begging for us to use the second translational property right there. And then the problem reduces to finding the inverse transform of this guy. That is our big F of S there. So what is the inverse transform of 1 over s squared plus 10s plus 26? Can we factor this? Should be the first thing that we're thinking. What two numbers multiplied together are 26 and added are 10? Who knows? And if you try to use the quadratic formula, you'll get complex numbers. So if it doesn't factor, then try completing the square. And if you complete the square there, that is s plus 5 squared plus 1. Those two are the same, as you can verify. And that makes it look like our Laplace transform of sine. It looks something like k over s squared plus k squared, except translated. So that is 1 over s minus negative 5 squared plus 1 squared. And now for this, we use our first translational property, where that is therefore e to the negative 5t times sine of 1t. Since this is 1 over s squared plus 1 squared, the sine of t, but translated to the left by 5. So employing this, we just stick that e to the negative 5t in front. So we got that f of s is that, and that the inverse transform of this part was e to the negative 5t times sine of t. So y, which is the inverse transform of the whole thing, is, by our second translational property, little f of t minus a times unit step of t minus a, which, well, the letter f is taken, so we'll call that big G. So we have little g of t minus 2 pi times unit step of t minus 2 pi, where little g is this. So we plug in. And we have this. This is our g of t minus 2 pi times u of t minus 2 pi. Okay, and this is completely correct. However, we can note that sine of t minus 2 pi is equal to sine of t because it has period 2 pi. So we could just replace that with sine of t. And that's what their answer does, although it wouldn't mark you wrong if you left the 2 pi in there. And only reason I put this here is that the way it has you input answers, it will have blank plus blank u of blank. And in this case, there is nothing over here. It's just something times u of something. So what you do then is you just put a 0 there. So indeed, you can see that this is what we got there and how we could input it. And that was our big F of S, our Laplace transform of y right there. So that is the Dirac delta function and solving problems with it. Have a great one.